Hello there. Welcome to the Science Owl Station channel. Today we journey toward a world that does not spin upright like Earth, not even proudly tilted like Mars, but instead lies almost completely on its side. A silent blue sphere that seems to roll around the sun like a celestial marble, drifting through the darkness in a posture unlike any other planet in our solar system. Right now, as you listen, imagine it suspended in the velvet black, a soft turquoise orb glowing faintly in reflected sunlight, tilted so dramatically that its North Pole and South Pole take turns pointing almost directly at the sun. It is a strange posture, nearly 98 degrees of axial tilt, as if some ancient cosmic hand gently tipped it over long ago, and it never quite recovered. Before we go further, tell me in the comments where you are listening from tonight, and what time it is where you are. Is it late evening? Early morning? Are you wrapped in blankets? Or sitting quietly at your desk? And if you enjoy slow, thoughtful journeys through the universe like this one, consider subscribing and leaving a gentle like. It helps this quiet corner of science continue to grow. Now let us drift closer. This world is called Uranus, named after the ancient Greek sky god, the primordial deity who personified the heavens themselves. In English, we pronounce it carefully, URANUS, softly, calmly, a name that echoes the sky. In Vietnamese, it is known as Sa Thien Vong, the King of the Heavens, a title that feels both regal and distant, fitting for such a remote and serene giant. Uranus is the seventh planet from the Sun. If we begin at the bright warmth of Mercury and travel outward past Venus, Earth, and Mars, past the great swirling storms of Jupiter, past the golden rings of Saturn, we arrive eventually at this pale blue world. It orbits far beyond the familiar inner planets, more than 2.8 billion kilometers from the Sun on average. At that distance, sunlight is faint, about 400 times dimmer than what warms your skin on Earth. And yet, even in that dim light, Uranus shines with a calm, bluish glow. It belongs to a special category known as ice giants. There are only two in our solar system, Uranus and its distant sibling, Neptune. They are different from the massive gas giants Jupiter and Saturn. While those worlds are dominated mostly by hydrogen and helium gas, Uranus contains a much larger proportion of heavier volatile substances, water, ammonia, and methane, substances astronomers gently call ices, though in truth they exist in exotic, compressed states deep within the planet. The term ice giant does not mean it is made of frozen snowballs. Instead, it refers to its internal composition, layers of dense, hot fluids rich in water and ammonia, surrounding a small rocky core. Uranus is both immense and strangely delicate in color, a frozen giant wrapped in blue light. But it is the tilt that captures our imagination first. 98 degrees. Imagine Earth tipped over so far that its poles traded places with its equator. Imagine the Arctic Circle facing the sun directly for months, for years, while the equator lay in twilight. That is the reality of Uranus. It does not simply lean. It almost lies down. Scientists believe this extreme tilt may be the result of a colossal collision long ago, perhaps a planet-sized object striking Uranus during the early chaos of the solar system. Over billions of years, the planet settled into its sideways spin, maintaining that unusual posture as it travels its long orbit around the sun. And so Uranus rolls. As it orbits, one pole points nearly straight at the sun for decades, bathing in continuous daylight, while the opposite pole sinks into a prolonged darkness. This is not a brief seasonal change like we experience on Earth. This is an epoch of light, followed by an epoch of shadow. The idea is almost dreamlike, a planet where sunrise might not come again for 21 Earth years. If you were somehow floating above Uranus now, you would not see dramatic stripes like Jupiter's, nor the golden rings of Saturn shining brightly. Uranus appears smoother, softer, more uniform. Its atmosphere hides much of its activity beneath a calm, nearly featureless veil. It gives an impression of stillness, of quiet patience. Yet beneath that calm exterior, it spins steadily. One rotation takes about 17 hours. So although it rolls sideways, it turns fairly quickly, day blending into night in less than one Earth day. There is something poetic about that, a world so dramatically tilted, yet turning in its own steady rhythm. And the name Uranus feels fitting. The sky god, the embodiment of the heavens, discovered in an age when humanity first began peering outward with telescopes, daring to look beyond what the naked eye could see. For thousands of years, people believed the solar system ended at Saturn. Then, quietly, patiently, Uranus revealed itself. Even tonight, as we speak softly of it, Uranus continues its sideways journey. No sound reaches us from there. No wind whispers across our microphones. Only reflected sunlight carries its color across the immense gulf of space. Picture it again now. A blue-green sphere, tipped gently onto its side, rolling slowly around a distant sun in a darkness so vast it feels almost infinite. The poles trade places with the sky. The seasons stretch for decades. This light is faint, but steady. Let that image settle in your mind. Wherever you are, let the world slow down for a while. Soften your gaze. Let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. There is something quietly beautiful about the idea that for thousands of years, Uranus was visible, faintly, barely, and yet unnoticed for what it truly was. It shimmered in the night sky at the very edge of human perception, so dim that it blended among the background stars, mistaken for just another distant point of light. And then, in the year 1781, a patient observer turned his telescope upward. His name was William Herschel. On the evening of March 13th, under the cool English sky, Herschel was conducting what he often did, careful, methodical sweeps of the heavens in search of double stars. His telescope was handmade, crafted with precision and dedication. As he scanned the sky, he noticed something unusual. A small disk, not quite star-like, not quite ordinary. At first, he did not claim a new planet. That would have been too bold. Instead, he believed he had found a comet. The object appeared to move slightly against the background stars, and comets were known wanderers. Herschel announced his discovery cautiously. Astronomers across Europe turned their own instruments toward this faint, shifting light. But as weeks passed, something did not fit. The orbit was too circular for a comet. Its motion too steady, too predictable. Gradually, the realization dawned. This was not a comet at all. It was a planet, a new planet. For the first time in recorded history, humanity had expanded the known boundaries of the solar system. Until that moment, Saturn had been the outermost known planet. For centuries, it marked the limit of the Sun's family. And then Uranus quietly redefined that boundary, pushing the edge of the solar system nearly twice as far out. The scale of our cosmic neighborhood suddenly grew larger, deeper, more mysterious. It is difficult to overstate how profound that discovery was. Imagine believing you understood the size of your world, only to learn it stretches far beyond your expectations. Uranus did not blaze into the sky with brilliance. It did not announce itself dramatically. It revealed itself gently, through patience and glass and curiosity. Herschel, filled with pride and gratitude toward his patron king, George III, proposed naming the new planet the Georgian planet. For a time, in Britain especially, it was called Georgium Sidus, George's star. The name lingered for decades in some regions. But astronomy, like the sky itself, belongs to everyone. Across Europe, many astronomers preferred a different approach, a name consistent with the mythological tradition established by the earlier planets. Mercury, Venus, Mars, Jupiter, Saturn, all bore names of Roman gods. And so the name Uranus emerged, suggested by the astronomer Johann Elert Bode. Uranus, the ancient Greek god of the sky, father of Saturn in mythology. The naming fit the cosmic lineage: Jupiter, Zeus, son of Saturn; Cronus, son of Uranus; Uranus. It extended the mythological family tree outward into space. It took time for the name Uranus to be universally accepted. Even into the mid-19th century, debates continued. But by around 1850, the name Uranus became standard across the astronomical world. The sky god claimed his distant throne. There is something fitting about that slow acceptance. Even the name of this planet arrived gently, gradually, without haste. And yet, what fascinates me most is that Uranus had likely been observed before Herschel, recorded in star charts as early as the late 17th century, but catalogued as an ordinary star. It was visible to the naked eye under dark skies, though barely. Its motion across the sky is so slow that over short periods, it appears stationary. For generations, it hid in plain sight. Only when someone looked carefully, patiently, did its true nature become clear. There is a quiet lesson there. The universe does not always shout its discoveries. Sometimes it whispers. Sometimes it waits centuries before we recognize what has been before us all along. When Uranus was confirmed as a planet, it marked the first time a new planet had been discovered using a telescope. This was not like the ancient identification of Mars or Jupiter, known since antiquity. This was modern astronomy in action: observation, calculation, confirmation. It was a triumph of scientific method, and it changed the way astronomers viewed the solar system. If one planet lay beyond Saturn, perhaps more waited even farther out. Indeed, decades later, careful study of Uranus's orbit would lead to the discovery of Neptune. Subtle irregularities in Uranus's motion hinted at another gravitational influence. The heavens were more complex than anyone had imagined. So from a faint blur in a telescope lens, the known universe expanded. Imagine Herschel standing in the cool night air, unaware that he was rewriting cosmic maps. The telescope steady, the sky quiet, the faint disk shimmering just slightly larger than a star. No fireworks, no cosmic fanfare, just a patient eye, a careful note in a journal, and a shift in humanity's understanding of its place among the stars. Even now, more than 2 centuries later, Uranus continues its slow orbit, unchanged by the excitement of its discovery. It does not know it was once mistaken for a comet. It does not know it once bore the name of a king. It simply turns, tilted and distant, beneath a faint sun. And perhaps that is the most soothing thought of all. The universe unfolds at its own pace. Planets wait quietly for us to notice them. Knowledge grows slowly, layer by layer, like light gathering at dawn. As you rest and listen, imagine that first discovery again. The telescope pointed upward, the faint blue world revealing itself gently against the darkness. A small shift in perspective, and suddenly the solar system is larger than it was yesterday. The sky feels deeper, the night feels wider, and Uranus continues its sideways journey, patient and serene. There is something humbling about a year that lasts longer than a human lifetime. On Earth, we measure our lives in seasons. Spring returning each year, summer warming the air, autumn softening the light, winter settling gently over the land. A year passes in 12 familiar months, but on Uranus, a single year stretches across 84 Earth years. 84. If a child were born today and somehow able to mark the beginning of a Uranian year, they would be well into old age before that distant planet completed one full journey around the sun. Generations rise and fall on Earth while Uranus moves slowly, patiently, through its immense orbit. At an average distance of about 2.8 billion kilometers from the Sun, Uranus travels along a vast elliptical path. The Sun, from that distance, appears much smaller, a brilliant star rather than a dominating disk. Sunlight takes nearly 2 hours to reach Uranus, compared to just 8 minutes to reach Earth. By the time it arrives, it is faint and gentle, carrying only a fraction of the warmth we know. And so Uranus drifts in a realm of cold light. Its orbital speed is about 6.8 kilometers per second, which may sound swift, yet in cosmic terms it is unhurried. The larger the orbit, the longer the journey. And Uranus's orbit is immense. Imagine drawing a circle nearly twice as wide as Saturn's path, tracing it slowly through the darkness. That is the track Uranus follows. Because of this great distance, the rhythm of time feels stretched. If you were standing somehow within its atmosphere, suspended safely in imagination, you would not experience the swift turning of seasons as we do on Earth. Instead, change would come almost imperceptibly over decades. The length of a Uranian year shapes everything about the planet's environment. Combined with its extreme axial tilt, those 84 Earth years create seasons unlike any other in the solar system. But even before we consider the tilt, the sheer duration of its orbit introduces a kind of cosmic patience. Think of it this way. Since Uranus was discovered in 1781, it has completed only about 3 full orbits around the Sun. 3 quiet revolutions in nearly 2.5 centuries of human history. Empires have risen and dissolved. Technology has transformed civilization. And Uranus has simply continued its steady path, completing just a few gentle laps around its distant star. There is something soothing in that scale of time. Its orbit is not perfectly circular, though it is not extremely stretched either. Like all planets, Uranus follows an ellipse. At its closest approach to the Sun, perihelion, it is slightly nearer, receiving marginally more sunlight. At its farthest point, aphelion, it drifts even deeper into the cold. But compared to some other celestial bodies, its orbital eccentricity is modest. The distance does not fluctuate dramatically. Instead, the tilt plays the greater role in shaping its seasons. Still, the long orbit ensures that each phase of sunlight and shadow endures for years upon years. If you imagine watching Uranus from afar, you would see it tracing its slow path among the background stars. Its motion is subtle against the constellations. Night after night, year after year, it shifts gently, so slowly that early observers mistook it for a fixed star. Only careful measurement over time reveals its wandering nature. And that wandering is steady, predictable, calm. Kepler's laws describe its motion with quiet mathematical elegance. The farther a planet is from the Sun, the longer it takes to complete its orbit. Uranus obeys this principle faithfully. Its 84-year year is simply the natural outcome of distance and gravity, the Sun's pull reaching outward, weaker yet persistent, guiding the planet in its endless loop. Gravity at that distance is softer than what Jupiter feels, yet strong enough to hold Uranus securely in the solar system's embrace. It does not drift freely into interstellar space. It remains bound, circling, always circling. And while it circles, it spins. Even as its year stretches across decades, its day remains comparatively brief, about 17 hours, as we will explore more deeply soon. So on Uranus, days pass quickly, even as years crawl forward with cosmic patience. There is a gentle contrast there. Fast days, slow years. Imagine living in such a rhythm. Sunrises arriving swiftly, one after another, while the larger arc of seasonal change unfolds so gradually that you might scarcely notice it within a single lifetime. The long orbit also means that Uranus receives far less solar energy than Earth, roughly 1/400th of what warms our planet. This contributes to its frigid environment, its pale coloration, its quiet atmospheric demeanor. The Sun is still present, still luminous, but distant and restrained. And yet, despite that distance, the Sun's gravity still defines Uranus's existence. Every second, the planet is falling gently toward the Sun, but because it is moving sideways at just the right speed, it continues missing it, curving around it endlessly. That balance between forward motion and gravitational pull is what we call orbit. It is a continuous falling, a perpetual dance. 84 Earth years for one graceful circuit. As you listen now, Uranus is somewhere along that path, perhaps slightly closer to the Sun than it was decades ago, perhaps slightly farther, but always moving, always tracing its elliptical journey through space. And in that slow movement, there is a kind of comfort. Time does not rush there. Seasons do not hurry. The Sun does not blaze fiercely. Everything unfolds at a pace so measured that human urgency feels almost irrelevant. Picture the planet again, tipped sideways, bathed in faint sunlight, drifting along its immense orbit, decades passing like quiet breaths, the year stretching long and silent. And in that vastness, there is stillness. If a year on Uranus feels almost endless, stretching across 84 Earth years in a slow and patient arc around the Sun, then a single day there feels surprisingly brief. Uranus completes one full rotation in about 17 hours and 14 minutes. In less than a single Earth day, it turns once on its axis, though that axis, as we have gently discovered, is tilted by an astonishing 98 degrees. So when we speak of a day on Uranus, we are imagining a world that spins sideways, like a wheel rolling along its orbit. Close your eyes for a moment and picture that motion. A pale blue sphere, tipped almost onto its side, turning steadily in the darkness. its equator does not align neatly with its path around the sun. Instead, it points almost toward it. The poles take their turn facing forward, then backward, as the planet rotates. And there is something even more curious. Uranus rotates in what astronomers call a retrograde direction. That means it spins opposite to the direction of most planets in our solar system. If you were observing from above the sun's north pole, you would see Earth spinning counterclockwise. Uranus, however, turns clockwise. It is not alone in this unusual behavior. Venus also rotates retrograde, but on Uranus, combined with its dramatic tilt, the effect feels even more otherworldly. Scientists believe this peculiar rotation may be another echo of that ancient collision we mentioned earlier. A massive impact long ago that not only tipped the planet onto its side, but may also have altered the direction of its spin. Over billions of years, Uranus settled into its present orientation, maintaining its quiet, sideways pirouette through space. Despite its strange posture, the rotation itself is steady and rhythmic. A Uranian day is shorter than an Earth day, yet not extremely fast compared to giants like Jupiter, which spins in just under 10 hours. 17 hours is moderate, neither hurried nor sluggish. But because of the tilt, the experience of day and night would be profoundly different from anything we know. On Earth, the sun rises in the east and sets in the west because of our rotational direction and upright axis. On Uranus, the path of the sun across the sky would be unfamiliar and deeply strange. During certain times of its long year, the sun might appear to circle the horizon rather than rise high overhead. At extreme seasonal phases, the sun could seem almost stationary in the sky, barely dipping below the edge of visibility. The poles, in particular, experience dramatic contrasts. For roughly 21 Earth years, one pole points almost directly toward the sun, bathing in continuous daylight. During that same period, the opposite pole remains in near total darkness. And yet, even in that prolonged light or shadow, the planet continues its 17-hour rotation. So imagine standing safely in imagination near one of those poles during its long summer. The sun would remain above the horizon for decades. But because the planet rotates, the sky itself would still shift. The stars would trace slow circles overhead. The sun might drift slightly in position, but never fully set. Day blends into day, without the relief of night. Then, decades later, as Uranus continues along its 84-year orbit, the geometry shifts. The sun slowly lowers, eventually disappearing for years at a time. The same pole that once basked in constant light now enters a long, deep twilight. This interplay between rotation and orbit creates a choreography of light unlike any other planet. The 17-hour spin continues faithfully, marking time in shorter increments, even as the broader seasonal cycle unfolds across generations. There is a gentle paradox in that rhythm. Days pass quickly, years pass slowly. If you were keeping a clock on Uranus, you would watch the planet rotate again and again, over 43,000 rotations during a single Uranian year. The small rhythm repeating within the vast one, the immediate turning within the grand orbit. And yet, because Uranus lacks a solid surface, this rotation is measured by tracking features in its atmosphere and magnetic field. Beneath the upper cloud layers lies a thick envelope of fluids and exotic ices, moving and shifting under immense pressure. The rotation is not something you could stand upon. It is a motion sensed through observation, through instruments, through subtle variations in radio emissions and atmospheric patterns. From afar, though, the image remains simple and serene. A blue world turning sideways in the dark. 17 hours. Not rushed, not frantic, just steady. And because of that sideways tilt, the rotation sometimes causes the planet's equator to point nearly toward the sun, rather than facing perpendicular to it as Earth's does. During equinox periods, which occur only twice in each 84-year orbit, the sun shines directly over Uranus's equator, and day and night briefly become more evenly distributed across the planet. These equinoxes are rare events in human timescales. The last occurred in 2007. The next will not come for decades. Think about that. A single equinox on Uranus is separated from the next by 42 Earth years. The rhythm of light there feels almost geological in its pacing. And yet, beneath that slow dance of seasons, the planet spins every 17 hours, like a quiet heartbeat, rotation after rotation, marking time in a way that feels almost comforting. As you rest and listen, imagine that steady turning. The faint sunlight brushing across the blue atmosphere, the planet rolling gently along its orbit, the sky shifting slowly overhead. A day begins, a day ends, another begins. Far away, silent and patient, Uranus continues its sideways spin. If there is one feature that makes Uranus feel almost dreamlike, it is the way its seasons unfold. Not in months, not even in years, but across decades. Because the planet is tilted by 98 degrees, nearly lying on its side, the changing of seasons is unlike anything we experience on Earth. Here we know the gentle rhythm. A few months of warmth, a few months of cold, daylight gradually lengthening, then shortening again. On Uranus, the same process stretches across an immense canvas of time. Each season lasts about 21 Earth years. Pause for a moment and let that settle in your mind. A single summer on Uranus spans more than 2 decades. A winter endures just as long. Spring and autumn are not fleeting transitions but slow, almost imperceptible shifts in light. When Uranus reaches one extreme of its orbit, one of its poles points almost directly at the sun. During that period, the pole experiences continuous daylight for roughly 21 Earth years. The sun never sets. It simply circles in the sky or hovers at a consistent angle depending on latitude. The opposite pole, meanwhile, sinks into a prolonged night, a darkness that can last just as long. Imagine living in such a world. At the North Pole during summer, you would grow accustomed to an endless day. No sunrise, no sunset, just a steady glow, faint but persistent, illuminating the pale atmosphere. Over years, the sun would very slowly shift position, tracing a gentle arc that takes decades to complete. Then gradually you might barely notice, the geometry changes. As Uranus continues its 84-year orbit around the sun, the angle of illumination begins to shift. The once fully lit pole starts to tilt away. The sun lowers slowly toward the horizon over years, not hours. Eventually, after more than 2 decades of constant light, it slips below the horizon and does not return for another 21 years. It is a kind of twilight that stretches across generations. The equatorial regions experience their own unusual rhythm. During solstice, when one pole faces the sun directly, The equator lies along a boundary between light and darkness. As the planet rotates every 17 hours, different regions pass through illumination, but the contrast between hemispheres remains dramatic. Only during equinox, which occurs twice during each orbit, does the sunlight fall more evenly across the planet. At that time, both hemispheres receive similar amounts of light, and day and night become more balanced. But equinox on Uranus is rare in human terms. 42 Earth years separate one equinox from the next, so seasonal balance is an infrequent event. Most of the time, Uranus exists in a state of extreme contrast, one half bright for decades, the other half shadowed. This extraordinary seasonal cycle affects atmospheric behavior. During equinox periods, astronomers have observed increased cloud activity and storms, perhaps triggered by the changing patterns of solar heating. When sunlight redistributes across the planet, the atmosphere responds. Subtle shifts in temperature can drive winds and cloud formation in ways that remain only partially understood. Yet despite these changes, the overall appearance of Uranus remains relatively calm compared to Jupiter or Saturn. Its cloud bands are faint. Its storms, though present, are less dramatic in visible light. The planet often looks smooth and uniform, as though wrapped in a serene blue haze. But beneath that tranquil appearance, seasonal energy slowly accumulates and redistributes. 21 years of continuous sunlight gradually warm one hemisphere. 21 years of darkness allow the other hemisphere to cool even further. The result is a planet that breathes on a timescale we rarely comprehend. Think of Earth's seasons as a quick inhale and exhale. Uranus's seasons are more like a long, measured breath that spans decades. Light lingers, darkness lingers. Nothing changes quickly. If you were observing Uranus from space over the course of a human lifetime, you would witness only a fraction of a single seasonal cycle. Perhaps you would see one hemisphere gradually brighten while the other dims. Perhaps you would note subtle shifts in cloud brightness. But the full arc of change, from one extreme solstice to the next, would outlast most observers. And there is something profoundly calming in that slowness. Our world often feels hurried. Days rush past. Years blur together. But Uranus reminds us that time can also stretch. That transformation does not need to be sudden. That light can linger gently before yielding to shadow. Picture the planet again. Tipped sideways, one pole bathed in long, pale sunlight, the other wrapped in quiet darkness. Slowly, almost imperceptibly, the balance shifts. The sun's angle changes by fractions of a degree each year. The transition from summer to winter unfolds so gradually that it feels almost eternal. 21 years of day, 21 years of night, and then the slow turning continues, carrying the planet onward in its immense orbit. As you listen now, Uranus is somewhere within one of those long seasons. Perhaps one hemisphere is gradually emerging from darkness. Perhaps another is settling into extended twilight. The process is so gentle, so patient, that from Earth we observe it only as a faint variation in brightness. Let that image rest in your mind. Decades of sunlight brushing softly across a distant blue world. Decades of shadow following in quiet succession. A rhythm of light and darkness stretched across 84 years, unhurried, unfolding slowly in the cold outer reaches of the solar system. If we could gently gather Uranus into view beside Earth, placing the two worlds side by side in the quiet of imagination, The difference in scale would feel both astonishing and serene. Uranus has a diameter of approximately 51,118 kilometers. That makes it about 4 times wider than Earth. If Earth were a small marble resting in your palm, Uranus would be closer in size to a large grapefruit. Smooth, cool-toned, softly luminous. But diameter alone does not tell the whole story. Volume increases with the cube of size. Because Uranus is 4 times wider than Earth, it contains about 63 times Earth's volume. Imagine 63 Earths fitting inside that pale blue sphere. Oceans, continents, clouds, mountains, multiplied many times over, yet all enclosed within a single distant giant. And yet, despite its immense size, Uranus is not the most massive of the outer planets. It is actually slightly less massive than Neptune, its neighboring ice giant. Uranus contains about 14.5 times the mass of Earth, while Neptune edges slightly higher. The difference is subtle but measurable, a reminder that size and mass are not always identical in scale. Its average density is about 1.27 grams per cubic centimeter, only a little denser than water. This relatively low density tells us that Uranus is not composed primarily of heavy rock and metal like Earth. Instead, it is dominated by lighter materials, hydrogen, helium, and those exotic planetary ices we spoke of earlier. Imagine holding something so large yet comparatively light for its size. A world immense in volume, but not overwhelmingly dense. Its gravity at the cloud tops is about 89% that of Earth's surface gravity. So if you could somehow stand, safely suspended, at the level where atmospheric pressure matches Earth's, you would feel slightly lighter than you do here. Your movements would be subtly eased, as though your body weighed just a bit less. Of course, Uranus offers no solid ground to stand upon. Its visible surface is simply the upper boundary of thick atmospheric layers. Beneath that lies deeper atmosphere, then layers of compressed fluids and exotic matter. But for comparison, scientists define a notional radius at the point where atmospheric pressure equals 1 bar, similar to Earth's sea level pressure. That is the level from which its size is measured. From that boundary downward, the planet grows denser, warmer, and more pressurized. But from afar, all we see is the outermost shell, a pale blue sphere floating in darkness. The sheer scale of Uranus becomes even more striking when we consider distance between planets. If we placed Earth at one end of a large field, Jupiter would loom enormous nearby. Saturn would appear grand but slightly smaller. Uranus, though smaller than those giants, would still tower over Earth, a cool and dignified presence in the outer reaches. Yet, because it lies so far away, it appears small in our telescopes. Distance shrinks giants into faint points of light. From Earth, Uranus shines at the edge of naked eye visibility under very dark skies. It does not dominate the heavens like Venus or Jupiter. It whispers rather than proclaims its presence. And perhaps that is fitting. Its immensity is quiet. Consider also that Uranus's equatorial circumference stretches over 160,000 kilometers. If you could travel around it at the speed of a commercial airplane, flying continuously without rest, it would take weeks to circle the planet once. The scale is almost beyond ordinary comprehension. Its mass, 8.68 times 10 superscript 2 kilograms, exerts a gravitational pull strong enough to hold 28 known moons in orbit, along with a system of faint rings. It shepherds them quietly as it circles the sun, maintaining order within its domain. And yet, despite all this mass and size, Uranus remains less dominant than Jupiter or Saturn. It does not command the solar system with overwhelming gravitational authority. It occupies a more reserved role, distant, stable, steady. When astronomers compare Uranus to Neptune, they often note that Neptune is slightly denser and radiates more internal heat. Uranus, by contrast, emits very little excess heat compared to the energy it receives from the sun. This relative lack of internal warmth contributes to its reputation as one of the coldest planets in the solar system, something we will explore soon in greater detail. But here, for a moment, let us simply rest in the idea of scale. A sphere 4 times wider than Earth, 63 Earths in volume, 14 Earths in mass, floating billions of kilometers away. This presence is immense, yet softened by distance. Its gravity steady, yet gentle compared to the giants nearer the sun. If Earth feels like a vibrant blue marble teeming with life and motion, Uranus feels like a vast, quiet ocean of pale light, calm, restrained, expansive. Imagine approaching it slowly in a spacecraft. From afar, it would appear as a small bluish star. Gradually, it would swell in view, revealing its circular disk. Closer still, you would notice subtle shading in its atmosphere, faint bands, delicate variations in tone. But it would not roar with dramatic storms like Jupiter. It would not blaze with brilliant rings like Saturn. It would simply grow larger, filling your window with blue. And in that size, there is stillness. Even now, as it drifts through its 84-year orbit, Uranus carries that immense volume through space with quiet dignity. Its mass bends space gently around it. Its gravity shapes the motions of its moons. This presence adds balance to the architecture of the solar system. A giant but a soft one, large beyond everyday imagination, yet calm in appearance. Let that image settle beside you tonight. A vast blue sphere, for times the width of Earth, moving slowly in the outer darkness, steady and silent. If we could somehow peel back the pale blue veil of Uranus and drift gently downward, layer by layer, we would not encounter a solid crust like Earth's. There are no continents there, no mountains rising from a rocky surface, no oceans lapping against shores. Instead, Uranus is structured in deep, gradual transitions, atmosphere giving way to denser atmosphere, then to vast internal layers of compressed, exotic material. At its very center, scientists believe Uranus contains a relatively small rocky core. Compared to the planet's total size, this core is modest, perhaps only slightly larger than Earth itself. It is composed likely of silicate rock and metal, compressed under immense pressure. Temperatures there may reach several thousand degrees Celsius, though precise values remain uncertain. But this core does not dominate the planet's structure. It is wrapped in something far more expansive. Surrounding the core is a thick mantle composed largely of what astronomers call ices. Yet the word ice here can be misleading. We are not speaking of frozen cubes floating in water. Under the crushing pressures deep inside Uranus, water, ammonia, and methane do not behave as they do on Earth. Instead, they form a dense, hot fluid, sometimes referred to as a supercritical fluid, neither fully liquid nor fully gas, but something in between. This mantle layer may account for the majority of the planet's mass. Water molecules are squeezed tightly together, Ammonia and methane mix within this dense interior ocean. Temperatures and pressures are so extreme that these materials adopt exotic states of matter unfamiliar to everyday experience. Some models even suggest that deep within this mantle, water molecules may break apart into charged particles, creating conditions that contribute to the planet's unusual magnetic field, a feature we will explore more fully later. But for now, simply imagine a vast, internal ocean of compressed water and ammonia, heated not by sunlight, but by residual energy from the planet's formation and slow gravitational contraction. It is dark there. Light from the sun never penetrates so deeply. The pressures rise steadily as one descends, millions of times greater than atmospheric pressure on Earth. Above this mantle lies the outer envelope, a thick atmosphere dominated by hydrogen and helium. This outer layer transitions gradually from the deep interior fluids upward into the cloud tops that telescopes observe. There is no sharp boundary, no sudden surface. Instead, the planet grows less dense as one moves outward, until eventually the pressure matches what we define as 1 bar Earth-like atmospheric pressure. And that is where astronomers mark the radius of Uranus. From there upward, the atmosphere extends thousands of kilometers into space, thinning gradually. The idea of descending into Uranus can feel abstract, almost meditative. Imagine sinking slowly, weightless, through layers of pale blue mist. At first, the atmosphere is thin and cold. As you drift downward, pressure increases gently, then more insistently. The blue color deepens slightly. Winds may sweep past, moving in silent currents. Deeper still, clouds composed of methane ice crystals may appear, delicate formations suspended in the upper atmosphere. Beneath them, additional cloud layers likely exist, perhaps composed of hydrogen sulfide and ammonia. Each layer forms at a different altitude depending on temperature and pressure conditions. The structure is layered, yet blended. Hydrogen and helium dominate the outermost regions, accounting for the majority of the atmospheric mass. Methane, though present in smaller quantities, plays an outsized role in shaping the planet's appearance. It absorbs red wavelengths of sunlight, allowing blue and green light to reflect outward. That is why Uranus glows in its distinctive cyan tone. But as you descend further into imagination, the pressure becomes immense. Eventually, hydrogen and helium mix with the deeper mantle of water and ammonia. The boundary between atmosphere and mantle becomes less distinct. Matter behaves differently under such compression. Molecules interact in ways difficult to replicate in laboratories on Earth. Some researchers even propose that under these extreme pressures, carbon atoms from methane could be compressed into crystalline forms, perhaps even diamond rain falling slowly through the mantle. It remains a hypothesis, supported by experimental evidence under simulated conditions, but not directly observed. Still, the idea is quietly captivating. Diamonds forming in darkness, descending slowly through a superheated ocean of compressed fluid. At the very center, the rocky core rests, dense, hot, compact. It contains only a small fraction of the planet's total radius, yet it anchors the structure gravitationally. Around it, layers of ice extend outward for thousands of kilometers. Above them, the gaseous envelope expands gently into space. Unlike Jupiter or Saturn, which are dominated mostly by hydrogen and helium throughout, Uranus contains proportionally more of these heavier volatile compounds. That distinction is what defines it as an ice giant rather than a gas giant. Its interior is quieter in another sense as well. Uranus emits surprisingly little internal heat compared to Neptune. Many giant planets radiate more energy into space than they receive from the Sun, due to leftover heat from their formation. Uranus, however, radiates only slightly more energy than it absorbs. Why this is so remains one of the enduring mysteries of planetary science. Perhaps that ancient collision disrupted internal heat flow. Perhaps the internal layers inhibit efficient convection. Whatever the cause, the result is a planet whose interior seems comparatively subdued, less thermally active than its sibling Neptune. And so we are left with an image of structure rather than surface. A small rocky heart, a vast mantle of compressed water, ammonia, and methane, an outer shell of hydrogen and helium, all layered gently, merging into one another under pressure and time. No sharp boundaries, no solid ground, just depth, layer upon layer, descending into darkness. As you rest tonight, imagine that quiet internal world, a deep, blue giant composed of rock, fluid ice, and gas, held together by gravity, turning slowly in the outer reaches of the solar system. Planet without a surface, a structure of layers, floating silently in the dark. From a great distance, Uranus appears almost simple, a smooth, tranquil sphere washed in pale blue. It does not display the dramatic bands of Jupiter or the golden haze of Saturn. Instead, it wears a soft, even coloration, like a watercolor gently brushed across the canvas of space. That color is not accidental. It is the quiet signature of chemistry. The outer atmosphere of Uranus is composed primarily of hydrogen, about 83%, and helium, roughly 15%. These are the same light elements that dominate the Sun and much of the universe. They form a vast, invisible framework around the planet, shaping its structure and buoyancy. But it is the remaining fraction, a small yet powerful 2%, that defines its hue. Methane. Methane gas in the upper atmosphere absorbs red wavelengths of sunlight. When sunlight reaches Uranus, it contains all the familiar colors of the spectrum. As this light passes through the atmosphere, methane molecules selectively absorb the red portion. What remains, blue and green light, is reflected back into space. The result is that gentle cyan glow we observe through telescopes. It is a subtle transformation. No dramatic pigment, no painted surface. Just molecules interacting quietly with sunlight, filtering it, shaping it. If you could hover above Uranus and look down at its cloud tops, you would see a planet wrapped in a cool, almost icy tone. Not the deep royal blue of Neptune, but a lighter, softer shade. For many years, Uranus was thought to be almost featureless, a calm blue orb without much atmospheric activity. Modern observations, however, have revealed faint bands and delicate cloud structures hidden within that smooth appearance. High-altitude clouds of methane ice crystals form in the upper layers. Deeper down, clouds of hydrogen sulfide and ammonia may drift within the atmosphere, though these are not directly visible in most wavelengths. Each cloud layer forms where temperature and pressure allow specific compounds to condense, a quiet layering process shaped by physics and chemistry. The atmosphere transitions gradually from the thin outermost regions into thicker, denser layers below. There is no clear line where sky ends and interior begins. Instead, density increases progressively as one moves downward. Pressure builds gently at first, then more forcefully. And yet, despite the faintness of its visible features, Uranus is not still. Winds circulate, clouds drift, storm systems form and fade. But because the sunlight is so faint at that distance, about 400 times weaker than at Earth, the energy driving visible weather patterns is subtle. The atmosphere reflects that restraint. Sometimes, during equinox periods, bright cloud features become more noticeable. The redistribution of sunlight across hemispheres appears to stir the atmosphere slightly, producing transient storms or bright spots. These features are fleeting in planetary terms, but from Earth they can persist for weeks or months before fading. Even so, the overall impression remains one of calm. The upper atmosphere of Uranus is extremely cold. Temperatures near the cloud tops can fall to around -224 degrees Celsius, making it one of the coldest planetary atmospheres in the solar system. That cold is not solely due to distance from the sun. Uranus also emits very little internal heat compared to Neptune. The result is a subdued thermal profile, reinforcing the planet's tranquil outward appearance. When spacecraft cameras captured images of Uranus during Voyager 2's flyby in 1986, many viewers were struck by how smooth it looked. Compared to Jupiter's swirling storms, Uranus seemed almost blank. But improved telescopes and infrared imaging have since revealed that beneath that smoothness lies subtle complexity. Faint stripes aligned with its rotation, delicate variations in brightness, whispering winds shaping invisible currents. The planet's atmosphere extends thousands of kilometers above the defined radius. At higher altitudes, hydrogen and helium dominate. Lower down, methane concentration increases slightly. Temperature and pressure determine which compounds condense into clouds and which remain gaseous. Light interacts differently at various wavelengths. In infrared observations, Uranus reveals patterns not visible in ordinary light. Darker bands and brighter regions emerge, hinting at circulation patterns hidden beneath the blue veil. And yet, even with these details, the overriding impression is gentle. A blue world, wrapped in hydrogen and helium, tinted by methane, cold and distant. Imagine sunlight traveling across billions of kilometers of space, finally reaching the atmosphere of Uranus. The photons strike methane molecules. Red light is absorbed. Blue light continues outward, traveling back across the vast darkness until it reaches our telescopes, and eventually our eyes. What we see is not merely color. It is interaction. It is chemistry expressed as hue. And so the blue veil of Uranus is both literal and poetic. A veil of gases filtering light. A veil of cold air hiding deeper layers. A veil that gives the planet its serene identity among the outer giants. As you rest and listen, picture that pale sphere again. Smooth, luminous, quiet, its atmosphere stretching upward into space, gradually thinning, merging into the interplanetary medium. A world defined not by continents or oceans, but by clouds and gases and the way sunlight moves through them. Hydrogen, helium, methane, a simple composition, arranged in layers, reflecting blue light softly into the night. If we think of distance as a measure of cold, then Uranus resides in a realm where warmth fades almost completely. Far from the sun, Beyond the orbit of Saturn, sunlight arrives weak and diluted. But distance alone does not fully explain the profound chill that defines this world. Uranus is often described as the coldest planet in the solar system. Temperatures in its upper atmosphere can fall to around -224 degrees Celsius. That is colder than Neptune, even though Neptune lies slightly farther from the Sun. There is something quietly mysterious about that. Most giant planets radiate more heat into space than they receive from the Sun. They retain leftover energy from their formation, heat generated when gravity pulled gas and ice together billions of years ago. Jupiter glows faintly in infrared light because it still releases that internal warmth. Saturn does the same. Neptune, too, emits more energy than it absorbs. But Uranus is different. It emits very little excess heat. Measurements suggest that Uranus radiates only slightly more energy than it receives from the Sun, far less than Neptune does. This subdued internal heat flow contributes significantly to its frigid atmospheric temperatures. Why Uranus lacks strong internal heat remains one of planetary science's gentle puzzles. Some scientists suggest that the ancient collision that may have tilted the planet also disrupted its internal convection, trapping heat deep inside and preventing it from rising efficiently to the surface. Others propose that the internal layers may be structured in a way that inhibits the upward movement of warm material. Whatever the explanation, the result is clear. Uranus feels thermally quiet. Imagine hovering near the top of its cloud layer. The Sun, small and distant, casts a pale light. The atmosphere around you is thin, frigid, and faintly blue. Temperatures remain well below the freezing point of water, colder than Antarctica's harshest winter, colder than any naturally occurring place on Earth's surface. And yet, despite this extreme cold, Uranus is not frozen solid. The internal pressures are immense. Deeper layers are warm, even hot, due to compression and residual energy. But that warmth does not manifest strongly at the cloud tops. Instead, the upper atmosphere remains chilled and subdued. This low temperature affects the behavior of gases and clouds. Methane condenses into ice crystals at high altitudes. Other compounds form cloud decks deeper down, depending on pressure conditions. The atmosphere's chemistry unfolds within this cold environment, shaping subtle cloud structures and wind patterns. The frigid temperature also influences the density profile of the atmosphere. Cold gases are denser, settling gently downward unless stirred by wind. The energy available to drive dramatic convection, like Jupiter's towering storm systems, is comparatively limited. Uranus's atmosphere appears calmer in visible light partly because the thermal engine beneath it is weaker. Yet calm does not mean inactive. Winds still flow, clouds still form. Subtle storms occasionally appear, especially near equinox when seasonal sunlight redistributes energy across the planet. But the underlying tone remains restrained. It is as though Uranus breathes more slowly than its sibling Neptune. In infrared observations, astronomers measure the faint glow of Uranus's thermal emission. That glow is weaker than expected for a planet of its size. Neptune, only slightly farther from the Sun, radiates over twice as much internal energy relative to what it receives. The contrast between the two ice giants continues to intrigue researchers. Perhaps Uranus's interior stores heat inefficiently. Perhaps layered compositional gradients prevent convection. Perhaps the planet's early history left it fundamentally altered in ways we do not yet fully understand. For now, we simply observe and measure. Minus 224 degrees Celsius. A temperature so low that familiar concepts of warmth feel distant. If you could somehow stand within its upper atmosphere, insulated from pressure and wind, your breath would freeze instantly, your surroundings colder than any natural environment on Earth. And yet, the cold is not violent. It is steady, persistent, quiet. Sunlight still arrives, though faintly. Methane still filters that light into blue. Hydrogen and helium still swirl gently in slow currents. Beneath the cold cloud tops, deeper layers remain pressurized and warm, but the surface impression is one of crystalline stillness. Uranus reminds us that temperature is not simply a function of distance. It is shaped by internal structure, by heat flow, by history. A planet can lie closer than another yet feel colder, depending on how it stores and releases energy. And so, among the outer worlds, Uranus holds a quiet record, the coldest measured atmospheric temperatures in the solar system. Picture that cold now, not as a sharp sting, but as a vast, enveloping stillness. A blue atmosphere suspended in darkness. A sun reduced to a bright star. A world whose upper layers remain chilled and calm, year after long year. In that frigid sky, winds move, clouds drift, light reflects, but warmth does not rise strongly from within. A giant planet, vast in size, yet restrained in heat, cold and steady, drifting in the outer night. And yet, even in that profound cold, Uranus is not still. Beneath the pale blue veil, winds move with surprising strength. Though sunlight is faint and internal heat subdued, the atmosphere does not remain motionless. Instead, powerful currents sweep across the planet, some reaching speeds of up to 900 kilometers per hour. 900, faster than most commercial airplanes on Earth. Faster than the strongest hurricanes our oceans can produce. Imagine standing only in imagination within that frigid sky. The temperature hovers near minus 224 degrees Celsius. The sun is distant and small, and yet the air around you surges sideways in tremendous streams, racing across thousands of kilometers without interruption. These winds are driven by a combination of solar heating, internal dynamics, and the planet's rotation. Even though Uranus emits little internal heat compared to Neptune, subtle temperature differences between regions still generate pressure gradients. And when a planet rotates every 17 hours, that rotation influences atmospheric circulation through the Coriolis effect, organizing winds into broad east-west bands. Unlike Jupiter's dramatic stripes, Uranus's banding is faint, invisible light. But in infrared observations, subtle zonal patterns emerge, alternating wind belts that circle the planet parallel to its equator. The sideways tilt complicates this pattern. Because the poles sometimes face directly toward the sun for decades, heating is distributed in unusual ways. One hemisphere may receive continuous light while the other remains in shadow. Over long timescales, this asymmetry influences atmospheric circulation, producing seasonal changes in wind behavior. During equinox periods, when sunlight strikes the equator more evenly, increased storm activity has been observed. Bright cloud features, some as large as continents on Earth, appear temporarily in the atmosphere. These storms are not as towering as Jupiter's Great Red Spot, but they reveal that Uranus's sky can awaken when conditions shift. Methane clouds form high in the atmosphere, appearing as bright patches against the blue background. Deeper cloud layers, composed of hydrogen sulfide and possibly ammonia, move in slower currents beneath. Each cloud deck exists at a different altitude, shaped by pressure and temperature. The winds themselves vary with latitude. Near the equator, speeds differ from those at mid-latitudes or near the poles. Measurements indicate complex circulation patterns, with some regions experiencing prograde winds, moving in the same direction as rotation, and others retrograde relative to the planet's spin. And yet, despite these swift winds, the overall visual impression remains calm. Uranus does not display swirling vortices easily visible from afar. Its storms are subtler, often detectable only with careful observation and sensitive instruments. There is a quiet contradiction here. Extreme cold, high wind speeds, soft visual appearance. The planet teaches us that motion does not always require warmth. Even in a frigid atmosphere, pressure differences can drive powerful currents. The air may be thin and icy, but it is not static. Imagine those winds sweeping across the planet's vast circumference, racing unimpeded over thousands of kilometers. There are no mountains to block them, no continents to disrupt their flow. The entire globe is an ocean of gas. Wind becomes the dominant sculptor of cloud forms. Occasionally, astronomers observe transient storms, bright white features appearing suddenly and then fading over weeks or months. These storms may rise from deeper layers, where slightly warmer gases ascend and condense into visible clouds. They are reminders that beneath the tranquil blue surface lies dynamic movement. Yet compared to Neptune, whose storms can be darker and more dramatic, Uranus's weather feels restrained. Neptune radiates more internal heat, fueling stronger convection. Uranus, with its limited heat flow, generates fewer high-contrast features. Its storms are more subtle, its patterns more delicate. Even the sound of those winds, if we could hear them, would be strange. There is no solid ground for them to roar against. No forests to rustle, no oceans to crash upon shores. The winds sweep across endless atmosphere, their motion felt only as pressure and flow. 900 kilometers per hour across a world billions of kilometers away. And yet, from Earth, Uranus appears almost motionless. That is the perspective of distance. Through telescopes, we see a smooth disk, pale and quiet. We do not perceive the racing winds directly. We infer them from spectral shifts and careful tracking of cloud features. The planet's movement remains mostly invisible to the casual observer. There is something poetic about that hidden motion. A cold blue world, spinning sideways, orbiting slowly, while invisible winds rush across its face. Activity concealed within calmness. As you listen now, imagine those currents flowing steadily. Methane clouds drifting, subtle storms forming and dissolving. The atmosphere circulating in great bands around the tilted sphere. Cold air, fast winds, soft light. Uranus does not need dramatic color to be dynamic. Its energy moves quietly beneath a veil of blue. And so the frigid giant continues. Winds sweeping, clouds forming, storms whispering briefly before fading. All within a sky so distant that even its fiercest gust feels like a quiet breath in the outer darkness. Beyond the pale blue atmosphere, stretching outward in delicate arcs, lies something far more subtle than Saturn's luminous halos. A system of rings so dark and narrow that they remained hidden from human eyes until the late 20th century. Uranus possesses 13 known rings. They do not blaze brightly. They do not form wide, glowing bands easily visible through small telescopes. Instead, they are thin, shadowy structures composed of dark particles, orbiting quietly in narrow paths around the planet's equator. Their discovery in 1977 was almost accidental. Astronomers were observing a distant star as Uranus passed in front of it, an event known as a stellar occultation. As the planet moved between Earth and the starlight dimmed briefly. But before and after the main dimming, observers noticed additional, smaller dips in brightness. Something else was blocking the starlight. Those subtle flickers revealed the presence of rings, thin bands of material orbiting the tilted giant. Unlike Saturn's rings, which are composed largely of bright water ice particles reflecting sunlight vividly, Uranus's rings are darker, likely composed of radiation-darkened ice mixed with organic material. Their particles range in size from dust grains to chunks perhaps several meters across. The rings are narrow and sharply defined. Some are only a few kilometers wide, yet extend thousands of kilometers around the planet. Shepherd moons, small nearby satellites, help maintain their structure, gravitationally confining the particles and preventing them from dispersing. There are 13 rings confirmed so far, though they are often grouped into inner and outer systems. The brightest and most prominent among them include the Epsilon ring, which is the densest and most massive. Others are fainter, sometimes visible only through specialized imaging techniques. Because Uranus is tilted 98 degrees, its rings share that orientation. They orbit in a plane aligned with the planet's equator, meaning the entire ring system appears tipped sideways relative to the solar system's plane. From Earth, the appearance of the rings changes over time. When Uranus approaches equinox, its rings are seen edge-on from our perspective, becoming so thin that they nearly vanish from view. At other times, when the tilt presents them more fully, the rings open slightly, appearing as slender arcs around the planet. Imagine observing them up close. You would not see broad, glowing sheets like Saturn's. Instead, you would drift past narrow corridors of orbiting debris, particles moving silently in synchronized paths. Each fragment follows Kepler's laws, circling the planet under the influence of gravity. No collisions erupt dramatically. Most motion is orderly, stable. The rings likely formed from the remnants of shattered moons or leftover debris from the planet's early formation. Over billions of years, gravitational interactions shaped them into their present configuration. They are relatively young compared to the age of the solar system, perhaps only a few 100 million years old, though precise estimates remain uncertain. Because the ring particles are dark, they reflect little sunlight. This makes them difficult to observe. In visible light, they appear faint. In infrared wavelengths, they reveal more structure. Voyager 2, during its 1986 flyby, captured the first close images of these rings, confirming their narrow, dark nature. There is something restrained about them. They do not demand attention. They do not shimmer brightly in amateur telescopes. They remain subtle, almost secretive. And yet, their existence adds another layer of complexity to Uranus's identity. Tilted planet, cold atmosphere, swift winds, and a system of dark rings orbiting in silence. If you imagine drifting above Uranus's cloud tops and looking outward, you would see these rings extending like delicate threads across the sky. Against the backdrop of distant stars, they would appear as thin lines, composed of countless small fragments, each one reflecting faint light. Because the planet's equator is nearly perpendicular to its orbital plane, the rings experience dramatic seasonal changes as well. At certain points in the 84-year orbit, one side of the rings receives prolonged sunlight while the other remains in shadow. Their illumination shifts slowly, just like the hemispheres of the planet itself. The entire ring system, then, participates in Uranus's unusual dance of light and darkness. And like the winds in the atmosphere, the rings remind us that motion continues even where calm seems dominant. Each particle circles at precise velocity, completing an orbit in mere hours. While Uranus takes 17 hours to rotate once, many ring particles complete their circuits in shorter times, racing along invisible tracks. Silent, ordered, persistent, 13 rings, dark and narrow, a faint halo around a distant blue world. As you listen tonight, picture them, thin bands encircling a sideways planet, turning gently in the outer solar system. Not brilliant like Saturn's, but quiet and understated. Rings that whisper rather than shine. And in that subtlety, there is beauty. If the rings of Uranus form delicate threads around the planet, then its moons are like quiet companions, small worlds traveling faithfully in orbit around the tilted giant. So far, astronomers have identified 28 natural satellites circling Uranus. Each one moves along a path aligned with the planet's equator, sharing its unusual 98-degree tilt. The entire system, planet, rings, and moons, rotates together in that sideways orientation, like a cosmic wheel rolling gently through space. There is something poetic about the names of these moons. Unlike the moons of Jupiter or Saturn, which are named primarily after figures from Roman or Greek mythology, the satellites of Uranus draw their names from literature, characters created by William Shakespeare and Alexander Pope. Titania, Oberon, Umbriel, Ariel, Miranda. These 5 are the largest and most prominent among Uranus's moons. Their names evoke forests, spirits, and distant realms, fitting for icy bodies drifting in the outer darkness. Titania is the largest moon of Uranus, with a diameter of about 1,578 kilometers. It is roughly half the size of Earth's moon. Its surface is composed largely of water ice mixed with rock. Observations reveal vast canyons and fault lines, suggesting that Titania once experienced internal activity, perhaps driven by tidal heating early in its history. Oberon, slightly smaller than Titania, orbits farther out. Its surface appears dark and heavily cratered, marked by ancient impacts preserved in the cold vacuum of space. Like Titania, it is composed primarily of ice and rock. Umbriel is darker still, one of the least reflective of the major moons. Its surface bears numerous craters, some with bright central features that contrast against the otherwise muted terrain. It seems geologically older, with fewer signs of resurfacing. Ariel, by contrast, appears brighter and more geologically complex. Its surface shows signs of valleys and ridges, suggesting past tectonic or cryovolcanic activity. Among the larger moons, Ariel may have been more internally active in its early history. And then there is Miranda, Miranda is the smallest of the 5 major moons, only about 470 kilometers in diameter. Yet its surface is among the most dramatic. Voyager 2 revealed enormous cliffs and patchwork terrain, as though pieces of different landscapes were stitched together. One cliff, known as Verona Rupes, rises perhaps 20 kilometers high, making it one of the tallest known cliffs in the solar system. The moons of Uranus are composed primarily of water ice mixed with rocky material. They likely formed from a disk of debris surrounding the planet long ago, perhaps the remnants of earlier moons shattered by collisions. Over time, gravity gathered that debris into the satellites we observe today. Smaller moons also orbit within and near the ring system, acting as shepherds. Their gravity helps maintain the narrow structure of the rings, preventing particles from dispersing. These moons are irregular in shape, often only a few tens of kilometers across, and are far less studied than the larger 5. Because Uranus rotates sideways, its moons orbit in a plane that is nearly perpendicular to the solar system's plane. If you could view the Uranian system from afar, you would see a miniature solar system tipped on its side, moons circling in a vertical orientation relative to the Sun. Their orbital periods vary. Miranda completes an orbit in just about 1.4 Earth days. Titania takes around 8.7 days. Oberon, farther out, requires over 13 days to circle the planet once. Each follows a predictable path, guided by gravity's steady influence. From the surface of one of these moons, if you could stand there, Uranus would dominate the sky. It would appear enormous, filling much of the horizon with its pale blue glow. Because the moons are tidally locked, always showing the same face to the planet, Uranus would remain nearly fixed in the sky, hanging like a vast turquoise disk above icy terrain. The light from the distant sun would cast long shadows across frozen landscapes. Craters would remain unchanged for eons, preserved in the cold vacuum. Unlike Earth's moon, which has been visited by humans, the moons of Uranus have been seen up close only once, during Voyager 2's brief flyby in 1986. Since then, telescopes have provided additional data, but no spacecraft has returned for a closer look. And so these moons continue their quiet revolutions, largely unobserved, orbiting a planet that itself moves slowly through space. 28 companions, ice and rock, named after characters from poetry and drama. Miranda's cliffs, Titania's canyons, Umbriel's dark craters, Ariel's ridges, Oberon's distant orbit. Each one contributes to the serene architecture of the Uranian system. Together, they form a family that reflects the planet's unusual orientation: tilted, orderly, patient. As you listen tonight, imagine those moons circling the blue giant. Small icy spheres tracing steady paths in a sideways plane. Uranus glowing softly at their center. A system of literature and ice, orbiting quietly in the outer solar system. Among all the quiet companions that circle Uranus, 2 moons invite us to linger a little longer in imagination: Miranda and Titania. One small and dramatically scarred, the other larger, composed and silent. Together they reveal that even in the cold outer solar system, landscapes can be complex and unexpectedly beautiful. Let us begin with Miranda. Miranda is modest in size, only about 470 kilometers in diameter. If it were placed beside Earth's moon, it would seem small and fragile. and yet its surface tells a story of immense forces. When Voyager 2 passed by in 1986, it transmitted images that startled astronomers. Miranda did not look uniform or gently cratered like many other small moons. Instead, it appeared patchwork, as though different terrains had been pressed together from separate pieces. Some regions are heavily cratered, ancient and worn. Others appear smoother, marked by ridges and valleys. Vast coronae, oval-shaped regions of unique terrain, interrupt the surface like frozen whirlpools of rock and ice. And then there is Verona Rupes. This immense cliff may rise nearly 20 kilometers high. To put that in perspective, Mount Everest on Earth reaches about 8.8 kilometers above sea level. Verona Rupes is more than twice that height. If you stood at its base, safely in imagination, and looked upward, the icy wall would stretch into the black sky in silent enormity. How such a feature formed remains a subject of study. One possibility is that Miranda experienced tidal heating in its early history. Gravitational interactions with Uranus may have stretched and flexed the moon's interior, generating heat that reshaped its surface. Later, as the orbit stabilized, that heating diminished, leaving behind a landscape frozen in time. Miranda's gravity is weak, only about 1% of Earth's. A jump there would send you drifting gently upward, descending slowly back to the surface. The sky above would be dominated by Uranus, vast and luminous, filling much of the horizon. Because Miranda is tidally locked, the same hemisphere always faces the planet. Uranus would hang almost motionless in the sky, glowing blue against the darkness. Now let us turn to Titania. Titania is the largest moon of Uranus, nearly 1,600 kilometers in diameter. It is far more massive than Miranda and presents a quieter face. Its surface is marked by impact craters and long fault valleys that stretch across its icy crust. These valleys suggest that Titania once experienced internal expansion, perhaps as water within its interior froze and expanded, cracking the surface above. Unlike Miranda's dramatic patchwork, Titania appears more restrained. Its craters are numerous but not as densely packed as those on Umbriel. Some regions appear smoother, hinting at ancient resurfacing events. Titania's gravity is stronger than Miranda's, though still much weaker than Earth's. Standing there, again only in imagination, you would feel light but not weightless. Uranus would appear smaller in the sky than it does from Miranda, because Titania orbits farther out. Yet it would still dominate the view, a blue disk suspended against a background of stars. Both Miranda and Titania are composed primarily of water ice mixed with rocky material. Their densities suggest that rock makes up perhaps half their mass, the rest being frozen water and other volatiles. Beneath their icy crusts, there may once have been subsurface oceans, warmed briefly by tidal forces early in their history. Today, they are likely frozen solid, silent, and inert. What makes these moons especially intriguing is how little we truly know about them. Voyager 2 provided only a brief glimpse as it sped past the Uranian system. Its images captured portions of their surfaces, but not in complete detail. Since then, powerful telescopes have refined our understanding, but no spacecraft has returned to map them comprehensively. They remain distant worlds, only partially revealed. Miranda with its towering cliffs and fractured plains. Titania with its long valleys and quiet craters. Ice reflecting faint sunlight. shadows stretching across frozen terrain. Because Uranus's axis is tilted so dramatically, its moons share that orientation. They orbit in a plane nearly perpendicular to the solar system's main plane. From the perspective of the Sun, their paths look almost vertical. This sideways architecture adds another layer of uniqueness to the system. And yet, despite the unusual geometry, their motion is orderly. Each moon completes its orbit in predictable time. Miranda circles in about 1.4 days, Titania in about 8.7 days. Their gravitational dance is steady, governed by laws that apply equally in every corner of the solar system. Imagine watching from a vantage point above Uranus's North Pole. The moons would appear to circle in a vertical ring around the planet. Slowly, patiently, endlessly, Miranda rising and setting, Titania gliding farther out, the ring system forming a faint halo between them, all of it moving in silence. There are no atmospheres thick enough on these moons to carry sound, no winds to erode their cliffs, no rain to soften their valleys. Craters remain preserved for billions of years. The passage of time leaves only the slow accumulation of micrometeorite impacts. Miranda's cliffs cast long, unchanging shadows. Titania's valleys stretch across icy plains without disturbance. They are worlds paused in geological stillness. And yet, they orbit a planet that spins sideways, bathed in faint sunlight, wrapped in methane blue clouds. Together, they form a system both dramatic and serene. Landscapes carved long ago, now resting in cold quiet beneath a distant sun. As you listen, let your mind drift across Miranda's towering cliffs and Titania's frozen valleys. Imagine the vast blue presence of Uranus hanging above them, steady and luminous. Small moons, great cliffs, silent orbits, all part of a tilted world drifting in the outer dark. If we could see the invisible forces surrounding Uranus, we would discover that its magnetic field is just as unusual as its tilt. On Earth, the magnetic field emerges roughly aligned with the planet's rotation axis. It is generated by the motion of molten iron within the core, creating a relatively centered dipole, like a bar magnet running through the planet from pole to pole. Uranus does not follow that pattern. Its magnetic field is tilted about 60 degrees relative to its rotation axis. Not only that, it is offset from the planet's center by nearly 1/3 of its radius. This means the magnetic field does not originate symmetrically from the middle. It is skewed, displaced, asymmetric. Imagine placing a magnet inside a sphere but not centered. Imagine tilting it sharply so that its magnetic poles emerge at unexpected angles. That is, in essence, the geometry of Uranus's magnetosphere. This unusual configuration was one of the most surprising discoveries made by Voyager 2 during its 1986 flyby. Instruments detected that the magnetic field lines were not aligned neatly with the planet's axis. Instead, they rotated dramatically as Uranus spun, creating a magnetosphere that wobbles through space. Because Uranus rotates every 17 hours, this tilted magnetic field sweeps around like a lopsided lighthouse beam. As the planet turns, the magnetosphere corkscrews outward into the solar wind, the steady stream of charged particles flowing from the sun. The result is a magnetosphere unlike any other in the solar system. On Earth, our magnetosphere shields us from harmful solar radiation. It channels charged particles toward the poles, producing auroras, shimmering curtains of light in high-latitude skies. Uranus also experiences auroras, but their geometry is far more complex due to the offset and tilt of its magnetic field. Instead of being centered neatly around the geographic poles, Uranian auroras can appear at unusual latitudes, shifting as the magnetic field rotates. Observations from space telescopes have detected faint ultraviolet auroral emissions, subtle glows in the upper atmosphere triggered by charged particles interacting with methane and hydrogen. Picture that for a moment. A pale blue planet, tipped sideways, surrounded by an invisible magnetic cocoon that is itself tilted and off-center. As it spins, the magnetic poles trace loops in space, guiding charged particles into the atmosphere at shifting locations. Faint auroras flicker high above the cloud tops. Delicate, ultraviolet glows against the cold darkness. The source of this strange magnetic configuration likely lies deep within the planet's interior. On Earth, the magnetic field arises from convection in a molten iron core. But Uranus's core is relatively small, and much of its interior consists of that vast mantle of water, ammonia, and methane in exotic states. Scientists propose that the magnetic field may be generated not in a central core, but in a shell of electrically conductive fluid located above the rocky center. In this region, extreme pressures may cause water and ammonia to become ionized, capable of conducting electricity. As these fluids move and churn slowly, they create magnetic fields through dynamo action. Because this conductive region is not centered and not symmetrically shaped, the resulting magnetic field is likewise irregular. The magnetosphere of Uranus extends outward into space, forming a protective bubble against the solar wind. However, due to the planet's sideways orientation, the magnetosphere's shape changes dramatically over the course of its orbit. At certain points, the magnetic axis may align in unusual ways relative to the Sun, producing complex interactions with incoming solar particles. Even the tails of the magnetosphere, the elongated structures trailing away from the Sun, twist and spiral as Uranus rotates. Some researchers describe the magnetotail as forming a corkscrew pattern due to the combined effects of axial tilt and magnetic offset. It is a quiet complexity, invisible yet profound. If you could see magnetic field lines as luminous threads, you would observe them emerging from unexpected latitudes, looping through space in asymmetrical arcs, then reconnecting far from the planet. You would see the entire structure rotating every 17 hours, sweeping through the solar wind in rhythmic motion. And yet, from Earth, none of this is visible to the naked eye. The magnetosphere leaves no mark in ordinary light. Only instruments detect its presence, measuring charged particles, mapping magnetic intensity, tracing field geometry. There is something humbling in that invisibility. A vast magnetic system surrounds Uranus, shaping its space environment, guiding particles, generating auroras, and yet it remains unseen unless we look with the right tools. Tilted 60 degrees, offset from center, rotating every 17 hours, an asymmetric magnetic dance around a sideways planet. As you listen now, imagine that invisible cocoon, the cold blue world spinning slowly, magnetic lines sweeping outward, curving and twisting into the dark, charged particles drifting along those lines, colliding gently with the upper atmosphere, releasing faint flashes of ultraviolet light. A magnetic field that does not conform neatly, planet that does not stand upright, both skewed, both unique, and yet both steady, turning quietly in the outer reaches of the solar system. In January of 1986, a lone spacecraft approached the tilted blue giant. It had been traveling for nearly a decade, launched from Earth in 1977, sweeping past Jupiter and Saturn before continuing outward into the colder reaches of the solar system. Its name was Voyager 2. To this day, Voyager 2 remains the only spacecraft ever to visit Uranus. As it drew closer, the planet grew from a distant point of light into a resolved disk. Cameras turned toward it. Instruments began measuring magnetic fields, charged particles, atmospheric composition. For a brief moment in cosmic time, only a few days around closest approach, humanity had a close companion near Uranus. The flyby occurred on January 24, 1986. Voyager 2 passed within about 81,500 kilometers of the cloud tops. It moved swiftly, carried by gravitational momentum and precise trajectory planning. There would be no orbit insertion, no long-term observation, just a single pass, a quiet visit. The images returned to Earth showed a smooth, pale blue sphere. Compared to Jupiter's dramatic storms and Saturn's brilliant rings, Uranus appeared almost understated. Its atmosphere looked calm, nearly featureless in visible light. Some viewers even described it as serene. But within that calm, Voyager discovered complexity. It confirmed the existence of the dark, narrow rings first detected in 1977. It imaged several of the planet's major moons, including Miranda's dramatic cliffs and Titania's broad valleys. It measured the tilted and offset magnetic field, revealing one of the most unusual magnetospheres in the solar system. It also detected faint atmospheric features, subtle bands and cloud structures that hinted at underlying dynamics. Instruments measured wind speeds, chemical composition, and thermal radiation. The data painted a portrait of a planet both quiet and mysterious. One of the most surprising discoveries was the magnetic field's geometry, tilted 60 degrees from the rotation axis and offset significantly from the planet's center. This finding reshaped theories about how ice giants generate magnetic fields. Voyager 2 also measured the temperatures in the upper atmosphere, confirming that Uranus is among the coldest planets in the solar system. It observed the interactions between the magnetosphere and the solar wind, noting how the tilted configuration produced complex particle dynamics. The spacecraft's journey through the Uranian system was brief. After closest approach, it continued outward toward Neptune, which it would visit 3 years later. Uranus faded behind it, shrinking once again into a distant blue dot. And since that moment, no other spacecraft has returned. For nearly 4 decades, Uranus has remained unvisited by robotic explorers. Telescopes on Earth and in orbit have provided additional insights, but none have matched the intimacy of Voyager's passage. There is something almost poetic about that singular encounter. A small machine, built by human hands, traveling billions of kilometers through space, carrying instruments and antennas, passing silently by a tilted world, sending back images and data across hours-long radio transmissions. At the time of the flyby, radio signals took nearly 3 hours to travel from Uranus to Earth. Commands sent from mission control required similar time to arrive. The conversation between spacecraft and planet was slow, measured by the vastness of space. Voyager 2 continues its journey even now, far beyond the orbit of Pluto, traveling through interstellar space. but its brief visit to Uranus remains a milestone in planetary exploration. Since then, scientists have proposed new missions, orbiters that could map the planet and its moons in detail, probes that could descend into the atmosphere, instruments that could measure its internal structure more precisely. As of now, those missions remain in planning stages. Uranus waits patiently. Imagine standing on Miranda's surface during that 1986 flyby. Voyager 2 would have appeared as a tiny moving point against the stars, briefly glinting in sunlight before vanishing. Or imagine drifting above Uranus's cloud tops as the spacecraft passed by, its cameras capturing the blue sphere from only tens of thousands of kilometers away. A moment of closeness, then distance again. The data Voyager gathered still informs our understanding today. Measurements of atmospheric composition confirmed the presence of methane. Observations of wind speeds refined models of atmospheric circulation. Magnetic field data reshaped theories about internal structure. And yet, for all it revealed, Voyager also emphasized how much remains unknown. The interior structure of Uranus, the reason for its weak internal heat emission, the detailed geology of its moons, the full complexity of its magnetosphere. These questions linger, awaiting future exploration. Until then, Uranus continues its 84-year orbit, spinning sideways, surrounded by rings and moons, enveloped in cold blue atmosphere. Voyager 2's visit was like a single photograph taken during a long journey, a snapshot of a world that changes slowly, patiently. And somewhere in the outer darkness, the memory of that encounter remains, encoded in data archives, preserved in scientific literature, carried onward by a spacecraft now traveling between the stars. A brief meeting, quiet farewell, and a tilted blue giant left once more to drift in solitude. There is no place to stand on Uranus. It is a simple statement, but one that reshapes how we imagine the planet. When we picture worlds, we often imagine surfaces, ground beneath our feet, horizons stretching outward, landscapes defined by mountains or plains. Uranus offers none of these. If you were to approach the planet in a spacecraft and descend toward its cloud tops, there would be no moment when wheels touch soil. No solid crust would rise to meet you. Instead, you would enter layers of atmosphere that grow steadily denser as you fall. At first, the air would be thin and cold, hydrogen and helium mixed with traces of methane. The sky around you would glow pale blue, sunlight filtered softly through gas. As you descended further, pressure would increase gradually. The temperature, though still cold compared to Earth standards, would begin to rise. Cloud layers would appear, high methane ice clouds drifting in delicate formations. Beneath them, deeper clouds composed of other compounds would form hazy bands. There would be no clear boundary between sky and below, only a thickening. The deeper you go, the more the atmosphere presses inward. Pressure climbs from 1 bar to tens, then hundreds of bars. On Earth, even a few dozen bars of pressure would crush most structures. On Uranus, that increase continues relentlessly. At some depth, hydrogen and helium transition smoothly into the exotic mantle, that immense ocean of compressed water, ammonia, and methane. But even here, there is no sudden surface, no shoreline, just a gradual change in state from gaseous to supercritical fluid. Imagine sinking into that mantle. The temperature rises dramatically, Pressures reach millions of times those at Earth's surface. Molecules pack tightly together. Light from above cannot penetrate this far. Darkness becomes absolute. There is no bottom in the familiar sense. The fluid grows denser and denser as you descend toward the small rocky core at the center. Gravity would pull you inward steadily, but buoyancy within the dense fluid might slow the descent. The concept of falling loses its meaning when everything around you is fluid and pressure balanced. Eventually, at the very center, lies that rocky core, compressed, hot, dense. But reaching it would require traversing thousands of kilometers of hostile environment, far beyond any current technological capability. So Uranus remains a planet without a surface, at least not one we can define as solid ground. This absence shapes how we understand it. Weather systems move freely across the globe, unhindered by continents. Winds circle without obstruction. Rings orbit above a world that is entirely atmosphere and fluid beneath. And if we imagine sound there, though in reality it would not carry far in such extreme conditions, we would not hear waves crashing or leaves rustling. There are no oceans with shores, no forests, only layers of gas and fluid pressing inward and outward under gravity's steady pull. The phrase "falling into Uranus" becomes an image of endless descent. From pale blue sky to deeper blue haze, from thin air to crushing pressure, from cold upper layers to warmer interior depths. The concept is almost meditative, a gradual immersion into density. And yet, despite this lack of surface, the planet has structure. It has boundaries defined by pressure and composition. It has rotation, magnetic fields, winds, seasons. It is not shapeless. It is simply continuous in its layering. This continuity is what defines ice giants. They are neither purely gaseous nor solid. They exist in intermediate states, vast spheres of fluid under pressure, wrapped in atmospheres that blend seamlessly into their interiors. If we compare Uranus to Earth, the contrast is profound. Earth has a thin atmosphere over a solid crust, beneath which lie mantle and core. The transitions are marked by distinct boundaries. On Uranus, those boundaries blur. There is no place to plant a flag. And perhaps that, too, contributes to its sense of distance. It is a world we can observe and study, but not one we can imagine inhabiting easily. It resists familiar imagery. Still, it remains tangible in another way, measurable through gravity, visible through telescopes, mapped in magnetic lines and atmospheric spectra. A giant sphere of layered fluids, turning sideways in the dark. Imagine descending again, slowly, gently, through its upper clouds, watching the pale light fade, feeling the pressure mount, realizing there will be no ground to meet you, only deeper layers, stretching inward toward a hidden rocky heart. Planet without a surface, a world defined by depth, and above it all, faint sunlight reflecting softly from methane-tinted clouds, as Uranus continues its long orbit in silence. Far beyond the warmth of the inner planets, beyond the golden glow of Saturn's rings, Uranus continues its long and patient journey through space. Its orbit, vast and elliptical, carries it slowly around the Sun once every 84 Earth years. There is no haste in that motion. At an average distance of nearly 2.9 billion kilometers from the Sun, Uranus resides in a region where sunlight is faint and seasons stretch across decades. The Sun, from that vantage point, appears as a brilliant star rather than a dominating disk. Its light still governs the planet's orbit, but gently, like a distant conductor guiding a slow symphony. The orbit itself is not a perfect circle, but a mild ellipse. At perihelion, Uranus draws slightly closer to the Sun. At aphelion, it drifts a bit farther away. The difference is subtle compared to some other celestial bodies, yet over such immense distances, even subtle shifts translate into millions of kilometers. As it travels this path, Uranus moves at an average speed of about 6.8 kilometers per second. To us, that may sound swift, but in cosmic terms, it is measured and unhurried. The farther a planet lies from the Sun, the longer its orbital period, a principle described centuries ago by Johannes Kepler. Uranus follows this rule faithfully, its motion predictable and serene. Imagine watching it from high above the solar system's plane. The inner planets would whirl rapidly in tight circles near the Sun. Jupiter would sweep in broad arcs. Saturn would trace a wider ring still, and Uranus, tipped on its side, would carve a grand, slow circle farther out, maintaining its unusual orientation as it moves. Because of its 98-degree axial tilt, the orientation of Uranus relative to the Sun changes dramatically over the course of its orbit. During solstice, one pole points almost directly at the Sun. Decades later, the geometry reverses. These shifts are tied intimately to the 84-year orbital rhythm. From Earth, astronomers track Uranus's position against the backdrop of distant stars. Night after night, its motion is barely perceptible. Month after month, it drifts subtly across constellations. Only over years does its wandering nature become obvious. It is a reminder that movement does not always demand attention. Gravity binds Uranus to the Sun in a continuous fall, a delicate balance between forward motion and inward pull. The planet is always falling toward the Sun, yet always missing it, curving around in an endless arc. That balance creates orbit. Over billions of years, Uranus has repeated this path again and again. Since its formation roughly 4.5 billion years ago, it has completed only about 54 million orbits. By comparison, Earth has completed over 4.5 billion. The difference in orbital pace is profound. 84 years per revolution. That means that since the dawn of modern astronomy in the early 1600s, Uranus has circled the Sun only about 5 times. Since Voyager 2's flyby in 1986, it has not yet completed even half of a single orbit. Time stretches differently in the outer solar system. Imagine standing, again only in thought, on one of Uranus's moons, perhaps Titania. You watch the blue giant hanging in the sky, its rings faintly visible. The Sun remains small and distant. Days pass quickly, Miranda racing around in less than 2 Earth days. But the grand shift of seasons unfolds almost imperceptibly, tied to that long orbital journey. Light angles change slowly. Shadows lengthen over decades. The balance between hemispheres shifts gently as Uranus advances along its path. And beyond Uranus lies Neptune, tracing an even longer orbit. Beyond Neptune, the Kuiper belt extends into icy darkness. The solar system does not end abruptly. It thins gradually, fading into interstellar space. Uranus occupies a transitional region, far from the Sun, yet still firmly within its gravitational embrace. The outer darkness is not empty. It is structured by motion. Each second, Uranus advances along its orbit by several kilometers. Each hour, it travels tens of thousands of kilometers through space. And yet, because of the scale involved, the motion feels almost still. Picture it now: a pale blue sphere, rings encircling it, moons orbiting faithfully. The entire system moving together around the sun in a grand, silent loop. There are no abrupt changes in that motion, no sudden turns, only curvature, smooth and continuous. 84 years to return to the same position relative to the sun. A slow cycle repeating. As you listen tonight, Uranus is somewhere along that arc. Neither at beginning nor end, simply moving steadily, as it has for billions of years. The seasons unfolding in long breaths, its rings turning, its magnetosphere twisting gently into space. The orbit continues, measured, predictable, quiet, and in that slow repetition, there is a kind of peace. And so we return gently to the layers, a small rocky core resting deep at the center. Above it, an immense mantle of compressed water, ammonia, and methane. Above that, a vast envelope of hydrogen and helium. And finally, the pale blue clouds we see from afar, layer upon layer. Uranus is not defined by a surface, but by continuity, transitions so gradual that one state becomes another without sharp boundary. Rock yields to fluid, fluid yields to gas, gas thins into space, and through all these layers the planet turns. 17 hours for one full rotation, a steady spin sideways, consistent. While it rotates, its magnetic field, tilted 60 degrees and offset from center, sweeps through space in an invisible spiral. Auroras flicker faintly in ultraviolet light. Winds race at hundreds of kilometers per hour across the cold upper atmosphere. Yet the impression remains calm. 84 Earth years for one orbit around the sun. A year longer than most human lives. During that long circuit, one pole leans into sunlight for 21 years, while the other rests in shadow. Then they trade places. Light lingers, darkness lingers. The rings, 13 thin bands, orbit quietly in the equatorial plane, aligned with the planet's tilt. Dark particles circle in narrow paths, guided by shepherd moons. 28 moons revolve around the tilted giant. Titania with its valleys, Oberon with its craters, Ariel and Umbriel drifting in measured arcs, Miranda with its towering cliff, frozen and still. All of it moving together, rotation within orbit, moons within rings, magnetic fields within solar wind. Repetition defines this world. The same 17-hour spin again and again. The same 84-year orbit again and again. Seasons of 21 years of light, 21 of darkness again and again. Over billions of years, Uranus has repeated these motions countless times. It does not rush. It does not pause. It simply continues. The methane absorbs red light. Blue light reflects outward. The color remains steady. Cold persists near minus 224 degrees Celsius in the upper atmosphere. Internal heat remains subdued, quieter than Neptune's. Even the discovery of Uranus followed this theme of quiet repetition. For generations it appeared as a faint star. Only when someone observed carefully did its motion reveal itself. It had been moving all along, unnoticed yet faithful to its path. Voyager 2 passed once. A brief encounter. then distance again. The planet continues without interruption. If you imagine drifting above its cloud tops now, you would see a smooth blue sphere beneath you, winds flowing invisibly, magnetic lines curving silently outward, rings stretching thinly in space, moons tracing their patient arcs. There is no dramatic crescendo here, no sudden transformation, only steady motion, layer upon layer, rotation upon rotation, orbit upon orbit. The solar system itself turns in the galaxy, and within it Uranus turns around the sun, and within that Uranus spins on its side. Motions nested within motions, each following laws written in gravity and time. And as we draw towards stillness, let the details soften. A blue sphere, cold air, dark rings, distant sun, 17 hours, 84 years, 21 years of day, 21 years of night, numbers that repeat quietly in the dark. Imagine now that the planet recedes from view, shrinking gradually into a small turquoise dot. Its rings fade from sight, its moons become invisible, the sun becomes a distant glow beyond it. The outer solar system grows quieter still. Wherever you are, let the world slow down for a while. Soften your gaze. Let the hum of life around you fade. Picture that tilted blue giant continuing its patient journey, turning, orbiting, layered in ice and gas, wrapped in silence. There is comfort in that continuity, in knowing that far beyond our restless world, something vast and steady keeps its rhythm. And as Uranus completes another fraction of its long orbit tonight, you can let your thoughts drift just as slowly. Planet without a surface, a magnetosphere that tilts and sweeps, rings that whisper rather than shine, moons frozen in ancient stillness, all moving gently through the cold outer dark.